Good evening everyone, good evening. I welcome you all again to VJ Enthuse. I hope you guys are doing great, having a good time. So people, before starting the session, you can just let me know in the chat box if I'm audible and visible to everyone, right? Hello Chitra, hello Ram Kailash, hello Vichlavat, welcome back, hi Shalini, hello Selva. Just people give me some green signal from the chat box so that I'll get to know that I'm audible and visible to you properly. Yeah, I'm doing great, Chitra. I'm doing great. How are you? Just let me know first of all in the chats if I'm audible and visible to you. Hello Anil. Hello Pradeep. Hi Ashwarya. I'm doing good. How are you? Perfect. So people, as you all must be knowing, tonight we are going to do the part 2 from the chapter solid state, right? In the first part of the solid state, we talked about the different unit cells, right, in detail. And in the tonight's session, what we are going to do is we are going to talk about the close packing of constituent particles in the solid in 2 dimension and 3 dimension in detail, right? So before starting the session, the ones who are new to the channel, let me introduce myself. Well people, my name is Wassim Sir and I'm your chemistry master teacher writer on this VJ Enthuse channel, yeah? The ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this VJ Enthuse, right? So please do like the video, share the video with your friends and do subscribe to the channel as well, yeah? Yes, Ahari, these concepts are enough. Yes, exactly. These are enough. Perfect. So people, you can let me know in the chats if you guys are super duper excited for one more session, right? You can let me know in the chats if you guys are super duper excited about this session as well. Just let me know in the chats first. Let me see the josh of the session tonight, right? Thank you, Raja Pratap. Thank you. Just let me know fast, people. Just let me know fast, yeah? Dinesh, you can talk to the operational team about it, right? They'll be helping you out about this. Yeah? Perfect. So people, without wasting a lot of our time, let's get going. Let's get started directly with our tonight's discussion, right? So what are we going to talk about in the tonight's session? It's going to be all about the close packing. It is going to be all about the close packing, right? What is close packing all about? In case of solids, what is close packing all about? So first of all, in close packing, what we are going to do is we are going to arrange the constituent particles of the solid in such a way that the empty spaces in between the constituent particles must get minimized, right? In close packing, we are simply going to arrange the constituent particles of the solid in such a way that the empty spaces in between the constituent particles must get minimized, right? So people, this close packing of constituent particles in the solid is done in different types, right? The first type of close packing is what we call as one-dimensional close packing. One-dimensional close packing. Right? The second one is called as the two-dimensional close packing. And the third one is called as the three-dimensional close packing. Right? Out of all these packings which we are going to do over here in the tonight's session, right, we'll be talking about two-dimensional close packing and three-dimensional close packing in detail, right? We'll be talking about the 2D close packing and 3D close packing in detail, correct? See, 1D close packing, it's very simple. In this kind of a packing, in this one-dimensional close packing of constituent particles in the solid, we are going to arrange the constituent particles of the solid along a line, either along x-axis or along y-axis or along z-axis, right? Let's say these are the constituent particles of the solid, right? These are the constituent particles of the solid. Now, if I want to do the close packing of these constituent particles of the solid in one dimension, what I need to do is I need to arrange these constituent particles along a line, along x-axis or y-axis or z-axis in such a way that the empty spaces in between them must get minimized, right? So this kind of a packing is something which I call as close packing in one dimension, as you can see, right? These two particles are at the maximum closest distance, right? They cannot come further more closer, right? So this is first of all what I'll be calling as the close packing of these constituent particles of the solid in 1D. Why it's in 1D? Because I have arranged these constituent particles along a line, either along x-axis, or you can plot them along y-axis, or you can plot them along z-axis. What should be your main motive? Main motive is that the empty spaces in between the constituent particles must get minimized, right? People, if I select any of the particle among these particles, let's assume I'm selecting this particle, right? If I'll ask you how many other particles are touching this particular particle simultaneously, as you can see, this particle as well as this particle, these two particles are touching this particular particle simultaneously, and the number of constituent particles touching a particular particle simultaneously determines its coordination number. So remember, the coordination number of each particle in case of close packing in 1D is going to be 2, right? I hope you got it properly, right? So this was our first type of packing in which we arrange the constituent particles of the solid along a line. You can arrange them either along x-axis or y-axis or z-axis, but you have to keep one thing into your mind, that the empty spaces between the constituent particles must get minimized, right? Very simple. I'm sure it's clear to everyone. Perfect. Now, let's talk about the close packing in 2D in detail, right? Let's talk about close packing in 2D in detail, and later on we'll be talking about the close packing in 3D as well, right? So I'm marking the heading over here as close packing in 2D. Close packing in 2D. Close packing of constituent particles of the solid in 2 dimension, right? So first of all, from this topic itself, you can get one thing. I'm sure about it. You would have got one thing. That I'm going to arrange the constituent particles of the solid along a plane. In a plane, I'm going to arrange the constituent particles of the solid. In 1D, I was supposed to arrange the constituent particles of the solid along a line, along one of the axes, I must say. In case of close packing in 2D, I'm going to arrange the constituent particles of the solid along two of the axes, or you can say along one particular plane, right? So first of all, the first type of close packing in 2D is what we call as AAA type packing. AAA type packing in 2D. What is this AAA type packing in 2D all about? See guys, first of all, let's assume these are the constituent particles of the solid. I want you guys to take a note of all these things carefully, okay? Let's assume these are the constituent particles of the solid. So right now, I've arranged these constituent particles of the solid along, for example, x-axis, yeah? Okay. Let me call this row of particles as row A. I'm calling this row of particles as row A, correct? Now people, since I need to do the close packing in 2 dimensions, so I need to fix one more row just below it or just above it, right? I need to fix one more row of particles just below it or just above it. Now people, I've got two options. I've got two options to fix the second row particles. Either I'll be keeping the second row particles exactly below the first row particles, or I'll be keeping the second row particles in the depressions caused by the first row particles, right? The name of the first row is row A, so the name of the second row is also row A, so that means simply the second row must be identical to that of first row, right? Yes, second row must be identical to that of first row, which is only possible if the second row particles will be exactly below the first row particles. Then only I can call this row of particles again as row A, right? Now people, the name of the third row again is row A, right? As you can see over here. So third row must be identical to that of first and the second row, right? So I'm keeping the third row particles exactly below the first and the second row particles. Well people, this kind of arrangement, this kind of packing of the constituent particles in a plane is what I call as AAA type packing in 2D. This is called as AAA type packing in 2D. I'm sure it's clear to everyone, right? Now guys, one more thing. Let me take the center of this constituent particle. Let me take the center of this constituent particle, center of this one, and center of this one, right? I've chosen the center of these 4 constituent particles over here, yeah? Now what I'll be doing, let me join these centers like this. Let me join these centers like this. So basically, I got a square shape over here. I got a square shape over here, as you can see, right? People, one thing, if you can notice, if I repeat this square along all the axes, if I repeat this square along all the axes, on repeating this square along all the axes, can I say on repeating the square along all the axes, I'll be generating the whole crystal over here? Absolutely, right? So can I say this square is basically the basic structural unit which on repeating along all the axes generates the entire crystal lattice, right? Okay, so should I be calling this square as the unit cell over here? Absolutely, right? So in case of AA type packing in 2D, what kind of unit cell is generated? It is the square unit cell which gets generated in case of this packing. It is the square unit cell which gets generated in this packing, yeah? Okay, that's why this packing is also called as square closed packing in 2D. It's also called as square closed packing in 2D. Square closed packing in 2D. I'm sure it's clear till here, right? Okay. Now people, let me select any of the particle over here. For example, I'm selecting this particle. Let me select this particle. If I'll ask you how many other particles are touching this constituent particle simultaneously, you'll clearly see this particle, this particle, this particle, and this particle. These 4 particles are touching, these 4 particles are touching this particular particle simultaneously, right? And the number of constituent particles touching a particular particle simultaneously defines its coordination number. So what is going to be the coordination number of each particle in case of AAA type packing in 2D? The coordination number of each particle in case of AAA type packing in 2D is going to be 4. I'm sure it's again clear to you, right? Now the point is the unit cell which got generated over here. The unit cell which got generated over here, which is the square unit cell, right? I need to calculate the packing efficiency of this square unit cell. I need to get the packing fraction of this square unit cell over here. How will I be getting it, right? So in order to calculate the packing efficiency, right, before going into that part, you can let me know in the chats if it's clear till here. You can let me know in the chats if it's clear till here, so that I can move on to the packing efficiency, right? Let me know in the chats first if it's clear till here. Yeah, perfect. All right, guys, wonderful. Yeah. Okay, perfect, guys. All right, so let's see exactly how packing efficiency of this unit cell is to be calculated. Understand properly what I'll be doing, okay? Let me erase this part over here. Let me erase this part. Okay, let me erase this part. I'm sure you would have copied all this. Yeah. All right, guys. So first of all, these constituent particles are these are spherical in shape. These are spherical in shape, right? So if I look at this layer from the top, if I look at this layer of particles from the top, so these layer of particles, they won't be looking like spheres to me. They'll be looking like circles to me, right? As you can see, correct? Right? If I'll have the top view of this layer, they look like circles to me, right? They look like circles to me, correct? Now, how do I calculate the percent packing efficiency of this square unit cell, right? See, it is first of all the two-dimensional arrangement. It is the two-dimensional arrangement. So in order to calculate the packing efficiency, I'll be using one formula. What is that formula going to be? The formula is going to be area of the constituent particles inside the unit cell, divided by area of the unit cell multiplied by 100. This is the formula by means of which I'll be calculating the percent packing friction, or you can call it as the packing efficiency in this square unit cell over here, right? Now guys, first thing which I would want you guys to notice over here, What is that going to be? Understand. If you look at this unit cell, this is the unit cell which I'm talking about, right? If you look at this unit cell, this square unit cell, how many corners it has? It has 4 corners, 1, 2, 3, 4. So how many corner particles are there forming this unit cell basically? There are 4 corner particles forming this unit cell, right? If I'll ask you, what is going to be contribution of this? What is going to be contribution of this constituent particle towards the square? You can clearly see this constituent particle will be shared simultaneously with 4 other square unit cells like this, right? This constituent particle, let me change the color of the pen. This constituent particle in particular will be getting shared by 4 other unit cells simultaneously. So what is going to be the contribution of this constituent particle towards my unit cell? It's going to be 1/4. It's going to be 1/4. Or can I say 1/4 of the area of this constituent particle will be inside the square? Absolutely. 1/4 of the area of this constituent particle will be inside the square. Similarly, 1/4 of this constituent particle's area will be inside the square, right? And similarly, 1/4 of the area of this constituent particle will be inside the square, right? And similarly, people, 1/4 of the area of this constituent particle will be inside the square, right? Okay. Right? Now we will have a look. Packing efficiency will be equal to area of constituent particles inside the unit cell. See, this is the unit cell which is square in shape. Let's assume its edge length is equal to A. Its edge length is equal to A. Let's assume the radius of one constituent particle is R, right? Let's assume the radius of the constituent particle is equal to R. So what is going to be the complete area of this constituent particle? Complete area of this constituent particle is going to be simply pi r square, right? It's going to be pi r square. But only 1/4 of the area of this constituent particle will lie inside this unit cell. So I'll be multiplying this 1/4. I'll be multiplying this with 1/4. So what is this term all about? This term is basically that area of this corner particle. This term is basically that area of this constituent particle which lies inside the square. Similarly, how many such kind of particles do we have? I've got 4 such kind of particles, right? I'm multiplying this term by 4, right? So what is this whole term all about? This whole term is basically that area of all the constituent particles, which lies inside this square, right? Divided by area of the unit cell. Unit cell is square in shape, right? Area of the square, as you all must be knowing, is equal to side square, which is going to be A square multiplied by 100, correct? People, as I told you, the radius of the constituent particle is equal to R. The radius of the constituent particle is equal to R, right? See, from here to here, it's going to be A, right? From here to here, it's going to be A. Can I say, from here to here, it's going to be A. So A is going to be basically equal to R plus R, right? A is going to be equal to 2R. Simple, because these two particles are touching each other. So A is basically equal to 2R. So instead of A square, I'll be writing 2R square. 2R square is going to be equal to 4R square, right? This 4 and this 4 got cancelled. R square got cancelled. So finally, you are getting the value as pi divided by 4 multiplied by 100. And when you solve it, the value comes out to be 78.54%. What is meant by this term? This is basically the packing efficiency of the unit cell, right? It is the packing efficiency of this kind of the packing, okay? What is meant by it? It simply means out of the total area of the square, 78.54% area is covered by the constituent particles, right? Out of the total area of this square I'm talking about, right? Out of total area of this square, 78.54% area is covered by the constituent particles, right? In the middle, there is some empty space as well. If I want you guys to calculate the percentage of empty space, which I call as percentage of voids is simply going to be equal to 100 minus 78.54. The value comes out to be 21.46%, right? So this much area out of the total area of the square. This much area out of the total area of the square will be empty, right? And that empty space in the unit cell is what I call as the voids. So I got to know the percentage of voids as well, which is 21.46. I got to know the percent packing fraction or packing efficiency as well, which is 78.54%, right? I'm sure it's clear to everyone, right, people? You can let me know in the chats if it is clear to you, right? So that I can move on to the next kind of packing in case of your 2D, right? Let me know fast in the chat box if it is clear to everyone. Is it clear to everyone properly? All right, perfect. So let's get going. Let's move on to the next part of this one, right? See guys, exactly. This was your AAA type packing in 2D, right? Now let's move on and talk about AB packing in 2D. What this AB packing in 2D is all about. What all things we should know about this AB packing in 2D, right? Let's try to understand this. Understand this. See guys. First of all, let's assume these are the constituent particles. These are the constituent particles of the solid. Let me call this row of particles as the row A, right? Let me call the first row of particles as row A. Now the name of the second row is B. So that means first and second row, these are not identical. These are non-identical rows, right? So see, in order to keep the second row particles, I've got two options. Either I'll be keeping the second row particles exactly below the first row particles, or I'll be keeping the second row particles in the depressions caused by the first row particles, right? Okay. If I keep the second row particles exactly below the first row particles, the two rows will be identical. It will be AA packing, right? But I want it to be as AB packing. So second row must be different. Second row can be only different if the second row particles will be placed in the depressions caused by the first row. In the depressions caused by the first row, like this. In the depressions caused by the first row, like this, right? So I'll be calling this row of particles as row B particles, right? The first row was row A, the second row is row B. The third row is again going to be row A, right? So the third row is going to be identical to the first row, right? Third row is going to be identical to that of first row, like this. So I'll be calling third row again as row A, right? So people, whenever you see this kind of packing in a plane, whenever you see this kind of packing in a two-dimensional thing, you'll be calling this kind of a packing as AB packing in 2D. You'll be calling it as AB packing in 2D, right? Okay. Now what all things we have to understand in this packing, I want you guys to take a note of these things. Say guys, understand. If I select the center of this constituent particle, center of this one, center of this one, center of this one, center of this one, and center of this one, right? If I join these centers, I got one hexagon over here, right? This is one hexagon over here, absolutely. I got one hexagon over here. If I'll ask you, on repeating this hexagon in all the directions, if I repeat this hexagon in all the directions like this, right? On repeating this hexagon in all the directions, can I say I'll be generating the whole crystal lattice, right? So on repeating this hexagon, on repeating this particular hexagon along all the axes, I'll be generating the whole crystal lattice. And that basic structural unit, which on repeating along all the axes generates the entire crystal lattice, I'll be calling that as the unit cell, right? So over here, the unit cell is of what shape? The unit cell over here is of hexagon in shape, right? It is the hexagonal unit cell which I get over here, right? That's why this kind of packing is called as the hexagonal closed packing in 2D. That's why this packing is called as hexagonal closed packing in 2D, right? Now people, if I select any of the particles over here, for example, I'm selecting this particle. How many other particles are touching this particular particle simultaneously? You can check it out. How many other particles are touching this particular particle simultaneously? This one, this one, this one, this one, this one, and this one. So 6 other constituent particles are touching this particular particle simultaneously. So I can simply generalize a statement. The coordination number of each particle in case of AB packing in 2D is going to be 6, right? It's going to be 6, as simple as that, yeah? Okay, now, let's try to calculate packing efficiency of this unit cell. Let's try to calculate packing efficiency of this unit cell. First of all, let's assume the edge length of this unit cell is equal to A. Let's assume edge length of this unit cell is equal to A. Since these two particles are touching each other, from this center to the circumference R, from this center to this circumference again R, so A is basically equal to 2 times R, where R is the radius of the constituent particle, right? Absolutely. Now what I'll be doing is, I'll be calculating the percent packing fraction, or you can call it as the packing efficiency. I'll be calculating the packing efficiency of this hexagonal unit cell over here. Understand? It's again going to be, since it's a two-dimensional arrangement, so I'm using the formula as area of the constituent particles inside the unit cell divided by area of the unit cell multiplied by 100. This is the formula which I'll be using in order to calculate the packing efficiency of this hexagonal unit cell over here, right? Now we will understand. Properly understand. Okay. For example, if I talk about this particular constituent particle, right? With how many hexagons this particular particle has been shared? This particular particle will be shared with 3 other hexagons. How come? Have a look. There'll be one more hexagon like this, right? There'll be one more hexagon like this, okay? So if I talk about this particular particle in general, this particular particle is being shared between 3 hexagons. This is the first one, right? This is the second one, and this is the third one, correct? So this particular particle is being shared with 3 other hexagons over here. So I can say only 1/3 of the constituent particle, only 1/3 of this corner particle will be lying inside this hexagon. Similarly, only 1/3 part of this constituent particle will be lying inside this hexagon. Only 1/3 part of the constituent particle will be lying inside this hexagon. Similarly, everywhere you can see only 1/3 part of the constituent particle will be lying inside this hexagon, right? Okay, and people, there is one particle exactly present in the center, and this whole particle lies inside this hexagon over here. This whole particle lies inside this hexagon over here, right? I hope you are getting it properly. This whole particle is inside this hexagon, right? Now people, let's understand few important things over here. What do I need to calculate? I need to calculate packing efficiency, which is equal to area of constituent particles inside the hexagon. If I'll ask you, if I talk about this constituent particle, which is one of the corners of this hexagon, the total area of this constituent particle is pi r square. The total area of this constituent particle is pi r square, right? But only 1/3 of this constituent particle, is inside this hexagon. So I'll be multiplying this with 1/3. If I'll ask you, what is meant by this term? This term is giving me that area of the corner particle. This term is giving me that area of the constituent particle that lies inside the hexagon. Similarly, if I ask you, how many other corner particles do we have like this? We have got 6 corner particles. If I multiply this term by 6, so this whole term is giving me that area of all the corner particles, which lies inside this hexagon, right? Similarly, there is one particle which is completely inside this unit cell, right? So for that particle, I need to take the complete area pi r square, right? So if I ask you, what about this whole term? This is basically that area of all the constituent particles, right? This is basically that area of all the constituent particles, right? Which lies inside this hexagon, okay? Divided by area of the unit cell. That means area of the hexagon. Since the unit cell is hexagonal in shape, right? I need to divide it with the area of hexagon. So how do I calculate area of hexagon? Now that is the point. How do I calculate area of the hexagon? If I join this corner with this corner, if I join this corner with this corner, if I join this corner with this corner, right? Can I say a hexagon is made up of 6 equilateral triangles. Absolutely, a hexagon is made up of 6 equilateral triangles, right? Yes, absolutely. Hexagon is made up of 6 equilateral triangles. In your class 9th, I must say, you would have studied one formula. In your class 9th, you would have studied one formula by means of which we calculate the area of one equilateral triangle, right? Okay, area of one equilateral triangle is equal to root 3a square by 4. Since hexagon is made up of 6 equilateral triangles, so I'll be multiplying this with 6, I'll be getting the area of the hexagon. So can I say this 6 multiplied by root 3a square by 4, 6 multiplied by root 3a square by 4, it is basically the area of this whole hexagon, right? Absolutely, guys. So I can, instead of area of the unit cell in the denominator, I can write it as 6 multiplied by root 3, 6 multiplied by root 3 a square by 4, right? A square by 4. Since a is equal to 2r, so 2r ka square becomes 4r square divided by what? Divided by 4 multiplied by 100. People, as you can see over here, this is r square, this is r square, this is r square. R square, r square, r square gets cancelled everywhere, right? Yes? See guys, r square and r square got cancelled everywhere, and when you put the values of pi exactly in this expression over here, you'll be getting the value exactly coming out to be around 91%. If I'll ask you what is this 91% all about, what is meant by this term 91%? It simply means out of total area of the hexagon, 91% area is covered by the constituent particles, right? So what is going to be the remaining percentage of area which will be empty? Remaining percentage of area that is empty is what I call as the percentage of voids, which is going to be 100 minus 91, which will be approximately coming out to be 9%, right? So 9% area of the total hexagon will be absolutely empty. Yes, will be absolutely empty, right? And 91% area of this hexagon will be covered by the constituent particles, right? You can let me know in the chats if it is clear to everyone. Sumant, that will be continued tomorrow. That will be continued tomorrow. Okay. So if I ask you, the first packing in 2D that I showed you, that was AAA packing in 2D. The second kind of packing is ABAB packing in 2D, right? Where is the packing efficiency more? Packing efficiency is absolutely more in case of ABAB packing in 2D as compared to that of AAA type of packing in 2D, right? Okay, I'm sure every single thing is clear till here, right? So this was all about the two-dimensional closed packing, right? From this two-dimensional closed packing, once a question was asked in your JEE Advanced, right? What was that question all about? I remember the question. The question was like this. You were given with a two-dimensional arrangement. What was the arrangement all about? The arrangement was like this. Have a look. See guys, exactly what the arrangement was all about. This was the arrangement of the constituent particle that was given to us, right? The unit cell was square in shape. This was the unit cell which was square in shape, right? The edge length of this unit cell was A. Radius of the constituent particle was R. I was supposed to calculate the packing efficiency. of this unit cell, right? Can you give it a try? Let me know the packing efficiency of this kind of the two-dimensional arrangement, right? Whose unit cell is square in shape, right? Edge length is A, and at the same time, radius of the constituent particle is R, right? Give it a try. You let me know its answer in the chats only. Yeah? Give it a try properly first. Give it a try, guys. Give it a try. All right, let me solve it for you. Let me solve it for you, guys. Let me solve it for you exactly. See, first of all, this square unit cell, it is made up of 4 corner particles, right? It's made up of 4 corner particles. First corner particle, second corner particle, third one, fourth one, and the one at the center. One at the center, right? Okay. Now we will understand. I need to calculate the packing efficiency. How do I calculate the packing efficiency? There's a formula for it. What is the formula? Formula is, since it's a two-dimensional packing, it's going to be area of constituent particles inside the unit cell. Area of constituent particles inside the unit cell divided by area of the unit cell multiplied by 100. This is how we calculate the packing efficiency first of all, right? Now let's try to calculate the area of the constituent particles that lies inside the square over here, that lies inside the unit cell over here. Let's understand it. First of all, if I talk about this corner particle, its contribution towards this square, its contribution towards this unit cell is 1/4, right? If the area of this whole corner particle is pi r square, I'll be multiplying this pi r square with 1/4. So what is this term all about? This term is basically giving me that area, this term is giving me that area of the corner particle which lies inside this square, right? I mean, I'm talking about this area. I'm talking about this area. Similarly, there are 4 such kind of particles, 4 such kind of corner particles. I'm multiplying it with 4. So this whole term, now it's going to give me the area of all the corner particles. Now it's giving me area of all the corner particles which lies inside this square, right? Apart from these constant particles, there is a particle which is present at the center as well. I have to take its whole area into consideration, which is pi r square, divided by area of the unit cell, Now the point is, what is the area of the unit cell? Area of the unit cell is simply side square, but it's square, right? It's going to be a square multiplied by what? Multiplied by 100, right? Now what is this a over here? A is the edge length, right? A is the edge length. If I'll ask you, is A going to be equal to 2r? Over here in this scenario, A won't be equal to 2r, right? A will be definitely greater than 2r. Now the point is, how can I write A in terms of r? Well, people, it's simple. If I join this corner with this corner, see, from here to here, it's A. From here to here, it's A. So from here to here, hypotenuse. This is A, so this is going to be root of 2A, right? This is going to be root of 2A. Let me call this point as point A, let me call this as point B, let me call this as point C. So I got the AC length. AC length is basically equal to root of 2A, right? This AC length, since this particle is touching this center particle and the center particle is touching this particle at the same time, right? So if I ask you something like this, have a look. Have a look exactly, guys, what I'm going to talk about. See, from this center till the circumference, it's going to be r. From this center till the circumference, it's going to be r. From this center till the circumference, it's going to be r. From here to here, it's going to be r. So can I say this root of 2a is equal to r plus r plus r plus r. So root of 2a is basically equal to 4r, right? So from here, I can calculate a is going to be equal to 4r divided by root 2, correct? Now what I'll be doing, I'll be putting the value of a into this equation. So instead of a square, I'll be writing 4r divided by root 2 ka square. 4r divided by root 2 ka square, right? So this r square, and this r square gets cancelled out. And when you solve it exactly, the value comes out to be 78.54%. What is meant by this term? This is basically the percent packing fraction, or you can call it as the packing efficiency of this unit cell, right? Which was given to me. This kind of arrangement of constituent particle, 2D arrangement was given to me, right? And I calculated its what? I calculated its packing efficiency, which is 78.54. What does that mean exactly? That means out of the total area of the unit cell, out of the total area of the square, 78.54% area is covered by the constituent particles, right? Rest, if I talk about this empty space, what is the percentage of empty space? Percentage of voids in this arrangement. You can say percentage of voids in this arrangement is simply going to be 100 minus 78.54, which comes out to be 21.46%, right? 21.46%. I'm sure every single thing is clear till here, right? You can let me know in the chats if everything is clear so that I can move on to a few more important things. Let me know fast, people. Let me know fast in the chats if it is clear to everyone so that I can move on to Few more important things, right? Hello Rohit, how are you? Long time. Erwin, periodic properties I'll be taking after redox reactions, right? Once we are done with redox reactions, after that I'll be taking periodic properties only, right? Okay, I'm sure it's clear till here, okay? Let's try to solve certain questions first. Let's try to solve certain questions, then we'll be moving on to the next topic, right? Let's try to solve certain questions. In the last session, I gave you the analysis of the unit cells in detail, if you remember, right? For example, the question is like this. I've got a solid in which you have got four types of constituent particles, A, B, C, and D, right? A, B, C, and D, right? I've got a solid which has got four different types of constituent particles, A, B, C, and D, right? Let's assume A particles are present at the corners of the cube. A very simple question I'm giving you. A particles are present at the corners of the cube. B particles are present at the face centers of the cube. C particles are present at the body centers. And D particle is present at the edge center. D particles are present at the edge centers. What is going to be the formula of the compound? Let's try to solve these sort of questions. Very simple. See guys, in a cube, you have got 8 corners. In a cube, you have got 8 corners, 6 face centers, 12 edge centers, and 1 body center, right? This is something which you all must be knowing. What is the contribution of the corner particle towards the cube? The contribution of the corner particle towards the cube is 1/8, right? Yes. The contribution of face-centered particle towards the cube is 1/2. The contribution of edge-centered particle towards the cube is 1/4. The contribution of the body-centered particle towards the cube is 1. That's something which we have discussed earlier as well, right? Now see, A particles are present at the corners of the cube. What is the contribution of the corner particle? 1/8. Total there are how many corner particles? 8 corner particles. Multiplied it with 8, right? B particles are present at the face centers. Contribution of face-centered particle is 1 to 1/2. There are 6 face-centered particles in total. C particles are present at the body centers. Contribution of the body-centered particle is 1, and there is total only 1 body-centered particle in the cube. D particles are present at the edge centers. Contribution of the edge center is 1/4. Total there are 12 edge centers, right? Now let's try to solve it. This will come as 1, this will come as 3, this will come as 1, this will come as 3. So A1, B3, C1, D3 is going to be the formula of the compound. That's something which I was supposed to calculate. Let me know in the chats if you got to know how to solve these sort of questions so that I can move on and show you some different types of questions as well. Let me know in the chat box first of all. Right? It's a simpler one, right? I'm directly moving on to one more question. Let's say you got a question like this. You've got a solid which contains constituent particles A, B, C, and D. Let's assume A particles are present at the 25% of the corners of the cube. B particles are present at 75% of the face centers of the cube. C particles are present at the 50% of the edge centers. And D particle is present at the body center. What is going to be the formula of the compound? What is going to be the formula of the compound? Can you let me know fast in the chats? Yes? Can you let me know in the chats fast? What is going to be the answer of this question? See guys, it's again simple. A particles are present at the 25% of the corners. 25% means 1/4. 25% means 1/4. 25 by 100, 1/4. Contribution of corner particle towards the unit cell is 1/8. Total there are 8 corner particles, right? B particles are present at the face centers. Contribution of the face-centered particle is 1/2. Sorry. B particles are present at 75% of face centers. 75% means 3/4. Contribution of the face-centered particle is 1/2. Total there are some 6 face-centered particles, right? C particles are present at 50% of edge centers, right? 50% of edge centers. 50% means 1/2. Half. Edge center contribution is 1/4. Total there are 12 edge centered particles, right? D particle is present at the body center, contribution is 1. Total there is 1 constant particle, right? Now let's try to solve it. This 8 got cancelled, so it comes out to be 1/4. This is 2 1, this is 2 3, it's going to be 9/4, right? This value is going to be 3 by 2. This value is going to be 1. If I take the LCM of the denominators, LCM comes out to be 4. So I'll be multiplying this term with 4. I'll be multiplying this term with 4. I'll be multiplying this term with 4 and this term with 4 as well. So this will come out to be 1. This will come out to be 9. This will come out to be 6. This will come out to be 4. So what is going to be the formula of the compound? A1, B9, C6, D4. So this is basically the formula of the compound which I was supposed to calculate. I'm sure it's clear to everyone, right? Right, guys? Simple. Let me make one more similar type of question so that you understand it properly. Let's say I've got a question like this. I've got a solid in which you have got some 4 types of constituent particles, A, B, C and D. 4 types of constituent particles you have, okay? Let's assume A particles are present at the corners of the cube, B particles are present at the face centers of the cube, C particles are present at the edge centers of the cube, and D particles are present at the body centers of the cube. The question says something like this. If 2 corner particles, 4 face-centered particles, and 6 edge-centered particles are removed, what is going to be the formula of the compound? You can solve this on your own, I'm sure, right? Right, people? Say, A particles are present at the corners, right? What is the contribution of the corner particle? That's 1/8. Total, there are how many corner particles? Total, there are 8 corner particles. But out of 8 corner particles, 2 corner particles are missing. So out of 8 corner particles, if 2 corner particles are missing, I'll be left with only 6 corner particles. So I'm multiplying this term by 6. Right? B particles at face centers. Contribution of face centers is 1 by 2. Total, there were some 6 face-centered particles. But out of 6 face-centered particles, 4 are missing. So I'll be only left with 2 face-centered particles multiplied with 2, right? Similarly, contribution of the edge-centered particle is 1/4. Total, there were some 12 edge-centered particles. But out of 12 edge-centered particles, 6 edge-centered particles are missing. So I'll be left with only 6 edge-centered particles. I'm doing nothing with the body-centered particles. Contribution is 1. So total, there is only 1 body-centered particle, as you all must be knowing, right? So this A will come out to be 3 by 4. This will come out to be 1. This will come out to be 3 by 2. This will come out to be 1. Now do one thing. Take the LCM of the denominators. If you take the LCM of the denominators, you get the LCM as 4. So multiplying this term by 4, this term by 4, this term by 4, and this term by 4 as well, right? So this 4 got cancelled. This value comes out to be 3. This value comes out to be 4. This value comes out to be 6. This value comes out to be 4 as well. So the formula of the compound is going to be A3, B4, C6, D4. I'm sure it's again clear to everyone, right? Okay, you can let me know in the chats if it is clear to everyone so that I can give you one more pattern of this question, right? Just let me know fast in the chats so that I can give you one more. Okay, let me give you one more same type of question. The question is the same. It is just I'm making certain changes. See guys, A, B, C, D. A particles at the corners of the cube, B particles at face centers, C particles edge centers, D particles body center, right? The question says, if all the particles along 2 of the body diagonals, are removed, what is going to be the formula of the compound? First of all, if I make a cube over here, This is the cube which I'm making, right? This is the cube. Okay, let me take two of the body diagonals of the cube, right? Let me join this corner with this corner. So this is one of the body diagonal, right? Let me join this corner with this corner. So it's going to be one more body diagonal. So these are the two body diagonals which I've chosen, right? These are the two body diagonals which I have chosen, right? So these two body diagonals will be touching somewhere here at the center, which is what we call as the body center, right? If all the particles along two of the body diagonals are removed, so which all particles lie along the body diagonals? Which all particles lie along these two body diagonals? I'll say this particle lies along this body diagonal, this particle lies along this body diagonal, right? This particle, and this particle. So basically, if all the particles along two of the body diagonals are removed, so basically you are removing how many corner particles? You are basically removing 4 corner particles. And you are removing one body center as well. What is going to be the formula there? Now it's clear, I must say. See, A particles are present at the corners of the cube. Contribution of the corner particle towards the unit cell is 1/8, right? Total there are 8 corner particles, but out of 8, you are removing these 4 corner particles. So if you are removing 4, I'll be only left with 4 corner particles, so multiplying this with 4, right? B particles are the face centers. The contribution of the face centered particle is 1/2. The contribution of the face centered particle is 1/2. Total there are 6 face centered particles, and there will be 6 face centered particles because I'm doing nothing with the face centered particles, right? Edge centers, I'm doing nothing with the edge centers as well. 1/4 multiplied with 12, right? Body center, contribution is 1. There was one body centered particle over here, but that is being removed, so I'll be left with 0 body centered particles, right? So what is going to be the formula? This value will come out to be 1/2, this value will come out to be 3, this value will come out to be 3, right? If I multiply throughout by 2, this is 2, this is 2, and this is 2, I get the value over here as 1, over here I get the value of 6, over here value of 6. So A1, B6, C6, and D0 is going to be the formula of the compound. I hope this is clear to everyone, right? Let me know in the chats first if it's clear. Let me know in the chats first if it is clear to everyone. Yeah? Okay, let me give you one more question then. Let me see if we can solve this one or not. Now the question says, if all the particles along one of the body diagonal plane, are removed, what is going to be the formula of the compound then? What is going to be the formula of the compound then? I'm removing all the constant particles which lie along the body diagonal plane, right? First of all, what is the body diagonal plane? Let me show it to you exactly. This is the cube which I'm making over here. This is the cube which I'm making over here, right? If I select any of the body diagonal plane over here, right? What is going to be my body diagonal plane all about? What is going to be my body diagonal plane all about? See guys. See exactly what is going to be my body diagonal plane. For example, I'm joining this corner with this corner, and at the same time this corner with this corner, right? So it's not visible here. Let me choose it. Let me select it differently. Okay, let me select it differently. Let me put this one and this one. Okay, yeah. Let me not select this one. Just a second. Let me make it a little more clear to you. Let me make it a little more clear to you. I'm selecting one of the body diagonal planes, right? I'm selecting one of the body diagonal planes. So what I'll be doing, this plane I'm talking about. This plane I'm talking about, guys. Have a look. What is happening to this? Just a second. Okay, this plane I'm talking about. This is the body diagonal plane which I'm talking about, right? This is the body diagonal plane which I'm talking about. Let me show it to you properly. This is the body diagonal plane which I'm talking about. If I'm removing all the particles along this body diagonal plane, what is going to be the formula of the compound? What is going to be the formula of the compound? See guys, First thing, which all particles lie along this body diagonal plane? This corner particle, this corner particle, this corner particle, and this corner particles, right? So these 4 corner particles, they lie along this body diagonal plane. So basically, you are removing 4 corners. You are removing 4 corners, this one, this one, this one, and this one, right? This body diagonal plane, over here there'll be an edge center, right? Over here there'll be an edge center. Right here there'll be edge center as well. So these 2 edge centers, again you are removing. So you're removing 2 edge centered particles as well, right? At the same time, this body diagonal plane, it passes through the top face and the bottom face center as well. So you are removing 2 face centered particles as well, right? This body diagonal plane will be passing through the center, So you're removing 1 body centered particle as well. So these are the particles which are actually removing in total, right? See, A particles represent the corners. The contribution of the corner particle towards the unit cell is 1/8. Total, there were 8 corner particles. But out of 8 corner particles, you are removing 4 corner particles. So I'll be left with only 4 corner particles, multiplied it with 4, right? Contribution of the face-centered particle towards the unit cell is 1/2. Total, there were some 6 face-centered particles, but out of 6, you are removing 2. So I'll be left with only 4. So multiply this with 4. C particles are present at the edge centers. Contribution of the edge-centered particle is 1/4. Total, there were some 12 edge-centered particles, but out of 12 edge-centered particles, you are removing 2. So I'll be left with 10. Contribution of the body-centered particle used to be 1. There was 1 body-centered particle, but you are removing that as well. So I'll be left with no body center, right? So this value comes out to be 1/2. This value comes out to be 2. This value comes out to be 5/2, right? If you take the LCM of the denominators, LCM comes out to be 2. So multiplying this term by 2, this term by 2, and this term by 2, right? So this value comes out to be 1. This value comes out to be 4. This value comes out to be 5. So the formula of the compound is going to be A1, B4, C5, D1, right? Yes? Right, people? Not D1, sorry, it's D0, right? So this is the resulting formula of the compound which I was supposed to calculate. I'm sure it's again clear to everyone, right? So people, I hope you would have got a lot of concepts in the tonight's session, right? So with this, I end the tonight's session here, right? I'll see you guys soon with one more session from the chapter Solid State, in which we'll be discussing about close packing in 3D, radius ratio, and the defects as well, yeah? Okay? You Garura, what kind of motivation you want, bro? What kind of motivation you want exactly? Alright, so people, this was nice meeting you in the tonight's session. If you have not liked the video, please do like the video, share the video with friends, do subscribe to the channel, and do not forget to hit the bell icon as well, right? So with this, I'm taking a leave. I'll see you guys soon with one more session from the chapter Solid State, in which I'll be covering the defects, right? Till then, take care, God bless you all, and love you all. Take care, guys, bye.